Hello class, this is chapter 2 about chemistry, and this is the second video that we're doing, and this one we're going to talk about water and also acids and bases. So in the last video we did the basics of chemistry, atoms, matter, and all that sort of stuff. Hopefully that all made sense. The one specific molecule we're going to focus on in this chapter is water, because it is the most abundant molecule. Remember, it's not, so water itself is not considered an organic or a living molecule, but it is essential to life. And that's maybe kind of hard to understand. So let me explain what an inorganic versus an organic molecule is. So we're considered an organic organism, meaning that well, sometimes organic is also equivalent with life. So molecules can be put into two kind of big categories. Either inorganic or organic molecules. So inorganic molecules are molecules that don't contain carbon and hydrogen, and organic molecules are opposite. They are molecules that contain carbon, and that carbon has to be bonded to at least one hydrogen. So that's what makes an organic molecule an organic molecule. It has carbon and hydrogen. So carbon is sometimes considered the atom of life, the molecule of life. That's what life is built on, carbon-based life, versus inorganic molecules. Now if we look at water, water is made up of oxygen and hydrogen, and so that is those two things. Those two atoms, neither one is carbon. There is hydrogen, but there's no carbon. So this is an inorganic molecule. But it's still essential life, and it's the most abundant molecule in our body. 60-70% of our body is water. So let's look a little more closely at the water molecule. Here it is again. These are two different ways to draw or illustrate the water molecule. So the one on the right, we have kind of a bubble diagram here showing how the hydrogens and oxygen atoms interact. So if oxygen is here, remember that oxygen has, so if we were to draw out oxygen, or look at the periodic table, here's oxygen. We see that oxygen has an atomic number of 8, meaning that it has 8 protons, a mass number of 16, meaning that it has 8 neutrons. Remember, mass number minus atomic number tells us number of neutrons. In this case, there's no charge associated with it, so it has 8 electrons. Now if we take those 8 electrons and draw them around the oxygen atom, so 2 electrons would go in the inner shell. That would then leave 6 electrons to go in the next shell. Remember, the magic number is 8, so oxygen wants to have those 8 electrons, so it needs 2 more electrons. Now it can either steal those electrons from somewhere, or it can share those electrons. In the case of water, oxygen decides to share. Remember, hydrogen just has 1 electron and wants 1 more electron, and so it's willing to share that electron with oxygen, so that oxygen has 8 and each of the hydrogens have 2. So oxygen has 6 plus 1 here and 1 here. The sharing gives you 8, and then each of the hydrogens have 2 electrons. And we end up with this water molecule. Here's another way of drawing it. The straight line here represents, on the left, the straight line here represents a bond, meaning the sharing of 2 electrons, so the oxygen and hydrogen. Okay, so what is this? One other thing to recognize here is that notice that the oxygen and hydrogens are not straight across from each other. It's not a straight line. We have this kind of V-shaped molecule. And this is what makes water very important, because this is a covalent bond, because they're sharing electrons, but it's not an equal sharing. And that's because oxygen has a very strong pull for electrons. And so it actually has the electrons more of the time than hydrogen does. It's not an equal sharing. It's kind of like if you were to share with your older brother or older sister. So they'll share with you sometimes, but they're not gonna share fully. They want to kind of keep most of it to themselves. That's what happens here. And so what it ends up doing is it gives the water molecule a charge. So because the oxygen molecule has the electrons, more of the time it gets a slight negative charge, and it pushes the two hydrogens to the same side, and they get a slight positive charge. So this is what we call a polar covalent bond. A polar covalent bond, meaning that there's a slight charge associated with it. And this is very important because this is what determines the properties of water. This is what causes water to interact the way that it does. Because it's a polar molecule, water molecules are attracted to each other. So the slight positive charge is attracted to the slight negative charge of another water molecule. And so water molecules interact with each other. This is called a hydrogen bond. This is a very important bond and a very special type of bond, but it's also not technically a true bond. It's just an attraction between polar molecules. So it's not a true bond. But we'll see hydrogen bonds a lot in chemistry and in biology. Very important part. So water molecules all have hydrogen bonds, and depending on how many of those water molecules are bonded to the others will determine its properties. When none of these water molecules are bonded to each other, then water is in a gaseous form. It's in a steam form. When all of them are bonded, then it's a solid form. And then in between, some are bonded, some aren't. That's a liquid form of water. So this leads to what we call the properties of water. It gives water its characteristics. And these are characteristics of water. The first one is that water is a solvent. It's considered the universal solvent. And that means that a lot of things dissolve in water. Things that dissolve in water, we call those a solute. You take a solute, put it in a solvent like water, you end up with what's called a solution. So water is the universal solvent, and many things are the solutes in water, such as salt, such as sugar, etc. Things that are dissolved in water, we call them hydrophilic. Hydro meaning water, philic meaning love of. So hydrophilic means love of water. Anything that has a charge is going to be hydrophilic. So before we looked at salt. Salt is an ionic bond between chlorine and sodium, positive and negative charge. So if you take this salt and you put it into water, it's going to dissociate, and the positive sodium is going to be attracted to the slight negative charge of the oxygen atoms. The negative chlorine is going to be attracted to the slight positive charge of the water atoms. It's going to dissolve in water. It's hydrophilic. Anything else that has a charge will do the same thing. Now some things don't dissolve easily in water, and they're considered hydrophobic. Phobic meaning scared of or dislike of, and hydro meaning water. So what are some examples of things that are hydrophobic? What do you put in water and it doesn't mix? Well, the big things are oils. Any sort of oil, any sort of non-polar molecule is going to be hydrophobic. That'll become important later as we talk about some other things. Here's this example of the salt dissolving in water as we talked about. Here's the sodium, here's the chlorine, and how it dissolved. The next property of water is that it's cohesive and adhesive. This is the idea that water molecules will cling to each other. They're attracted to each other. That's why when water is dropping, it forms like a little droplet, or when rain falls, it forms a droplet because water molecules will cohere to each other. And then adhesion means that water molecules cling to other things. This is why when you go outside in the morning, you see the dew stuck on the spider web. That's adhesion. Another great example is if you have a very small, it doesn't even have to be small. If you have a cup or a water bottle or something like that, if you look at how that water is sitting in the water bottle, you'll notice that on the edges it goes up the water bottle just slightly. And that's adhesion. So on the edges of the water bottle, the water molecules are clinging and they're starting to move up. They can't move up really high because then gravity pulls them back down, but they slide. And the smaller you make that bottle, the higher the water will climb up. So that's an important part as well. Water has a high specific heat capacity and high heat of vaporization. This means that it takes a lot of energy to change the state of water. So water, because of these hydrogen bonds, it can absorb a lot of energy before it changes state. Same thing with well, let me give you an example first. So a great example of this is living by the ocean. So if you guys have ever gone to live by the ocean or a large body of water, the temperature is more mild around those areas, and that's because of the high heat capacity of water. So in the summer, when it's really hot, the water, the ocean, absorbs the heat. Then when it's cold in the winter, it slowly releases that heat, and so it keeps the temperature of the cities nearby the ocean very mild. High heat of vaporization. So if you want to boil water, for example, that takes a lot of energy to change that water into steam. You have to put in a lot of energy because it resists that change. Because in order to get to steam, as I said before, you have to break all of those hydrogen bonds. All of those hydrogen bonds have to be broken. So that takes energy to do that. These molecules have to be moving really fast. They don't have time to make those bonds. So it takes a lot of energy to go from liquid water to vapor water. The last thing to talk about here is this idea of acids and bases, and this is related to water as well. Because when water molecules, if they break up, you end up with this situation here where you have hydrogen ions. We call this a hydrogen ion because it has a charge. So what does a hydrogen ion look like? Well, if we go back to our periodic table, hydrogen has one proton, so when it has no charge, it has one electron. So in this case, we now have hydrogen with a positive charge. In order to have a positive charge, that means you have to have less electrons than protons. Hydrogen only has one electron. So in order to have a positive charge, that basically means that hydrogen ion has lost its electron. It's just a proton. A hydrogen ion is just a proton. This is a hydroxide. OH negative is a hydroxide ion. Now if you add these two together, you'll see that we come up with water. So here we have two H's and an O. We have a positive and negative. If those were to covalently bond, we end up with water. So water can break apart into hydrogen ions and hydroxide ions, or it can form back into water. And this is a process that's constantly going on in liquids. So the definition of an acid is a substance that has a lot of hydrogen ions, or just protons floating around. Bases are substances that have lots of hydroxide ions. So what this means is that acids and bases, so if you have an acid with lots of hydrogen ions, if you add a base to that, those are going to interact with each other and just form water. They're going to cancel each other out. So acids and bases can be strong or weak depending on the number of hydrogen or hydroxide ions. So if you have lots of hydrogen ions, it's going to be very acidic. Same thing with bases, it's going to be very basic if you have lots of hydroxide ions. So what we have is this thing called a pH scale that indicates how strong or weak an acid is. There's lots of different substances. Now human blood, we already mentioned that a little bit, so we have to maintain this very narrow range of pH around 7.35 to 7.45. Other things that are around us, seawater, egg whites. Now on a pH scale, 7 is considered neutral. That's the very middle, because the pH scale goes from 1 to 14. So if you have something that has a pH of 7, it's neither acidic nor basic, it's neutral. Anything less than 7 is going to be acidic, so milk is slightly acidic. We get into things like soft drinks, they're even more acidic. Black coffee, tomatoes are acidic. You get even more acidic with vinegar, lemon juice. Stomach acid, which is a type of hydrochloric acid, is clear down around 1. That means it's a very strong acid. Lots of hydrogen ions. Hydrochloric acid, even stronger. On the basic side, some things you may not be familiar with: baking soda, Great Salt Lake, milk of magnesia, household ammonia, oven cleaner, and then something called sodium hydroxide. So if you were to take something on the basic side and add it to something on the acidic side, then it's going to neutralize based on what it is. Now if you take sodium hydroxide and you add it to milk, milk is not acidic enough to neutralize sodium hydroxide unless you add a whole bunch, so it's still going to be slightly basic. On the other hand, if you take sodium hydroxide and mix it with hydrochloric acid, they're both about the same strength, one basic, one acidic, you're going to end up with neutral pH. So the reason this is important is because living things require certain pHs in order to carry out their functions, to be able to metabolize and things like that. We already talked about the normal pH of blood. If you have blood that has a pH less than 7.35, then we call this acidosis. If you have pH that's greater than 7.45, we call that alkalosis. So acidosis means, so if it's less than, if the pH is less, that means it's more acidic. If it's greater, then that's more basic. Neither of these is a good situation and has to be remedied. So how does our body remedy this problem? So let's say we get too acidic or we get too basic. How do we deal with this? Well, our body has to maintain homeostasis, and so we have a system set up called a buffering system where we maintain our pH by using other chemicals to neutralize the acids and the bases that might be added to our body. And so we're able to manage that. So we're able to keep our blood pH, for example, at a certain range by using these buffers. Here's an example of a buffer system. It's a bicarbonate carbonic acid buffer system. So let's say that you have extra hydrogen ions that you've added to your body. Well, we have this bicarbonate in our body, and what it'll do, it will react with the hydrogen ions and form carbonic acid. The other thing can happen, the other opposite direction can happen if you have a hydroxide ions. You add that to carbonic acid, and look, it dissociates into water and bicarbonate. So in this way, our body maintains. We can add a lot of acid to our body, and our body will buffer that to a certain point. And we can do the same thing with basic type of substances, and our body will buffer that. Finally, electrolytes. I mentioned electrolytes already. These are ions. And these are substances that release ions when they're put into water. So often if you buy bottled water at the store, they filter it, so they take everything out, and then they'll add back in electrolytes. So then that actually is what gives the water the taste when you're drinking water. Because that's a little bit about water and acid and bases. The next section we're going to talk about organic chemistry, the molecules of life.